Let's say we wanted to solve a logarithmic equation. Let's just remember that all the time, whenever you are dealing with a logarithmic expression, let's say log base b of some quantity, in order for this log to be defined, we need the quantity inside the log to be positive. So that's a key thing we need to remember. Whenever we are solving a logarithmic equation, we need to make sure that whichever potential answer we get at the end, we plug it back into the original equation and make sure that we do not create either the log base b, and that for any base of a negative number, or the log base b of the value 0. We want to, stay away from those possibilities because such logs are not defined. So any potential solution that leads to either the log, after you clean it up, the log of a negative number or the log of 0, you need to discard this potential solution and only keep the solutions that do check out in the original equation. Now, having said this, if we were to go ahead and solve this logarithmic equation, which we did do over here, if you were to start with this log equation, notice how nice it is because you have one log on one side and then a number on the other side. So what we do, let's remember we're going to do something called zapping the log. And then we'll have that this cancels on this side. So you just have x minus 4 on the left hand side is equal to 2 raised to the third power, 2 cubed, which is a value of 8. And you can just solve, this equation and then make sure that whichever solution you get, it checks in the original equation, giving you the same quantity on both sides. So it's easy when you just have one log equal to a number. Now let's go ahead and take a look at a more complex question, which I'm getting from the book. Let's go ahead and take a look at number 72 in our textbook right here, 72, and I just put that question with its direction on a Word document. So let's take a look at this more closely. We want to solve this logarithmic equation. We want to be sure to reject any value of x that is not in the domain of the original logarithmic expression. We want to give the exact answer. Then, where necessary, use a calculator to obtain a decimal approximation correct to 2 decimal places for the solution. So let's go ahead and see what we have for this logarithmic equation. Notice that we do have 2 logs showing up on the left hand side. So you have this log right here, this log right there, and that difference of 2 logs is equal to the number 1. So it would be ideal if those 2 logs could become a single log, and notice the base is 4. So if only I could write those 2 logs, combine them as just a single log, that's called condensing. That would be nice if I had log base 4 of something equal to 1. So let's go ahead and see how we're going to achieve that, which property of log we can use to combine 2 logs that are creating a difference over here into one single log. Let me refer you to the property of logs, which I'm going to display in just a second. So let's see which property of logs we're going to use. Since we want to combine 2 logs into as a single log, we're going to use our quotient rule. And since the base that we had is a general base, we're going to use the one with the base b being mentioned. So let's use this quotient rule, with our particular problem. So I'm just going to use this particular quotient rule. to make our two logs on the left hand side combine as into a single log. So those two logs will become a single log using what we call the condensation of logs, condensing the logs. So let's condense our logs. I'm going to put the formulas so we can see how to do that. Let's use this formula for condensing the logs, and we're going to use it on the left hand side. So let me position the pieces properly. So now I'm going to basically for this formula just borrow the right hand side. So now we do see that we do have two logs and they are separated by a subtraction symbol. The base we're dealing with is base 4 in this case. So those two logs, we're going to combine them, condense them as a single log, which we're going to write below. So we do get one single log, basically that will represent those two logs. After we condense them, the base still remains, the one we had, base B will be base 4. So let's go ahead and see how those two logs will become a single log. Okay. So let me just write the step in between. So what we get is the following. We get those two logs condensing as a single log. So we'll get a log base 4 of a quotient. Now this quotient, notice the quotient bar is right here in green. Then we need to talk about what m will be, the numerator. The numerator m is the quantity you see inside the log, which is preceding this subtraction sign. So m is x plus 2. And n, what we're dividing by, which I will write in gray, n is a quantity inside the log after the minus sign. So it's a quantity x minus 1. And that is still equal to 1 because we had those two logs combining, condensing as a single log using that property we mentioned. The quotient rule, the condensing of the quotient rule. So on the left hand side, we just use that quotient rule. So we don't need our rule anymore and we don't need our steps anymore. So we're just going to go ahead and concentrate on the given question we had and the next step. So let's get rid of our formulas and let's just proceed with solving now this simpler logarithmic equation where we do have one log on one side is equal to a number. So let me write it again just so we can have a clear view of what we're doing. And let me go ahead and zap my log. So what do we get on the left hand side? All of this is gone. So you just have the quotient which was inside the log. We have x plus 2 over x minus 1, which is in parentheses, but you really don't need the parentheses. And that is equal to 4 raised to the power 1, 4 to the first, which is really 4. So we need to go ahead and solve this simple equation, and we'll do that by cross multiplying. So we will have x plus 2 times 1, and let me do that over here. We have x plus 2 times 1 is equal to the product of those two, which is x minus 1 times 4. So this is x plus 2 on the left equal to, and you can distribute the 4x minus 4, and you can solve this simple equation, and you'll get that 3x minus 4 on the right is equal to 2 on the left. Let's just add a 4 to both sides, and we are solving 6 equal to 3x. Divide both sides by 3, and you get that 2 is what I call potential answer. I should not assume anything about this answer until I plug it in to make sure that it checks in the equation that's given to us. So if you take the original equation, do not take anything in between over here. No, just go back to the original equation given to you. So we have log base 4 of x plus 2 minus log base 4 of x minus 1, is that equal to 1? And we're going to check that when we replace x by 2. So instead of x, put a 2. So we're looking at finding if log base 4 of 2, taking the place of x, plus 2 minus log base 4 of, again, x being replaced by 2, and then minus 1, is that 1. So what we need to do is the following. We need to clean up those logs. So this is log base 4 of 2 plus 2, that's 4, minus log base 4 of 1, is that 1. Now the base is 4, so let's see if we can evaluate each one of those logs. Log base 4 of 4, I'm asking you which power should I put on the red base 4 in order to get the number 4, which is located inside the log. So which power of the red 4 would give me the 4 inside the log? It's power 1. 4 to the first is 4. So this log is worth over here. This log is worth a 1. Minus, now let's evaluate the second log. What is log base 4 of 1? Let me do that on the side in case that helps. So log base 4 of 1 is an exponent, such that if you raise the base 4 to that exponent, you will get the number inside the log. You would get a 1. So I'm asking you which power, which exponent should I put on this 4 in order to get 1? Which power of 4 gives me 1? And you would say, oh, I know what the answer is. It's 0. 4 to the 0 is 1. So that exponent, which is the value of log base 4 of 1, is 0. So what do we have? We're asking, is a 1 minus a 0 equal to a 1? And indeed, this is true. So our potential answer, which was x equal to 2, is really our answer. So x equal to 4, we like that answer. That's our solution. So our solution set, which we write with braces, will welcome that answer of 2. And that's our answer for this question. Do not believe that it will always work out. I'll show you something which you can check in the PowerPoint, a similar question. So in this question from the PowerPoint, notice we have similar questions, 2 logs, a difference of 2 logs over here equal to a number. Notice the 2 logs are separated by a subtraction sign. You condense them as a single log, then you zap over here the log, and you get an equation which gives you an answer. And when you check it, it doesn't work. So the solution set ends up being the empty set. So take a look at that.